Okay, we're going to talk about related rates today. First thing I want to do is go over steps to solving the related rate problems. So the first thing, draw a picture. I can't stress this enough. Name the variables that you have and your constants, and let t be time. I want you to make sure you write down the information that you know in terms of the named variables from number 1. Then I want you to identify what you want to find. Okay, the next thing is to write an equation that is going to relate all of your variables. Then at the end, you are going to evaluate using the known values to find the rate. So our first example, when a circular metal plate is heated in an oven, its radius increases at 0.02 centimeters per second. At what rate is the plate's area increasing when the radius is 50 centimeters? So you have a circular metal plate. So I'm going to draw sort of a little disc, and it has some radius. Now the radius is increasing at 0.2 centimeters per second. So that means dr dt, the change in the rate of the radius with respect to time, is equal to 0.2 centimeters per second. We want to find the rate that the plate's area is increasing. So we want to find dA dt. Now here's some notation that you might not be familiar with. You really need to notice this word when the radius is 50 centimeters. So I'm going to put this big vertical bar, it's a conditional, basically means when. So find dA dt when the radius is 50. So do not label r equals to 50 over here in our diagram, because if you did, then that would mean that it is 50 all the time. And this is expanding, so it is not constant. Now I need to write an equation relating them. Well, our variables are r and a. So we're talking about area, so hopefully you're thinking about a equals 2 pi r squared. So if I take the derivative with respect to time, so dA dt, I'm going to get 2 pi r dr dt. And so now I want to find our dA dt when r equals to 50. So that means now I can actually plug in the 50 and plug in my 0.2 for my dr dt. And I end up with 2 pi centimeters squared per second for our units. So let's try another example. The length L of a rectangle is decreasing at a rate of 2 centimeters per second, while the width W is increasing at a rate of 2 centimeters per second also. When L is 12 centimeters and W is 5 centimeters, find the rates of change of the area, the perimeter, and then the length of the diagonal of the rectangle. So we have a rectangle with length L and length W. The length is decreasing at a rate of 2 centimeters per second. So because it's getting shorter, it's decreasing. I have to use a negative 2 centimeters per second. We also know that the width is increasing, so dW dt equals 2 centimeters per second, positive 2 for this one. Now when L is 12 and W is 5, find the rates of change. So we're going to do one at a time. But again, do not label this 12 and 5 in your diagram, otherwise you're saying it's always 12 and always 5. Find dA dt when L is 12 and W is 5. So we'll write it as a conditional here at the bottom. So we need an equation relating everything. Well, this one should be easy. Area of a rectangle is length times width. So when we differentiate with respect to time, try to remember your product rule. So that's going to be dL dt times W plus dW dt times L. And since now we're trying to figure out what all this equals to, when we plug in L is 12, W is 5, we can get our answer. So dL dt is negative 2, W is 5, dWt is 2, and L is 12. Negative 10 plus 24, so 14 centimeters squared per second. Next thing we want to do is find the change in the perimeter, so dP dt. And again, when L is 12, W is 5. So in our rectangle, the perimeter equals to 2 times the length plus 2 times the width. So the derivative with respect to time is 2 dL dt plus 2 dW dt. Again, plug in your conditions. So 2 times dL dt, which is negative 2, plus 2 times dW dt. Your perimeter is not changing. Okay, one last one here for this problem. We want to find the change in the diagonal. I'm going to write this out as dd with a capital D, dt. Okay, so we need the diagonal in this diagram. And the diagonal is going to be the hypotenuse of this right triangle, so the square root of L squared plus W squared. So the diagonal was the square root of L squared plus W squared. Now I don't really feel like taking the derivative with that radical there, so I'm going to do something different. I'm going to square both sides and then take the derivative implicitly. So 2d dt equals to 2l dl dt plus 2w dw dt. So now figuring out everything when we plug in what we know. So that'll be 2 times, what's d now? We actually have to calculate this. That'll be a 5, 12, 13 right triangle, so hopefully you know that one, Pythagorean triple. So 2 times 13 times d dt equals 2 times 12 times negative 2 plus 2 times 5 times positive 2. So add everything all up, move them over, you're going to find that dd dt equals to negative 14 over 13 centimeters per second. I'll go ahead and do one more. So suppose the edge lengths of x, y, and z of a closed rectangular box are changing at the following rates. So dx dt equals 1 meter per second, dy dt equals negative 2 meters per second, and dz dt equals to 1 meter per second. I want us to find the rate at which the box's volume, surface area, and diagonal length, s equals to square root of x squared plus y squared plus z squared, are changing when x equals 4, y equals 3, and z equals 2. Alright, so we have a rectangular box. So let's identify our sides as x, y, and z. And then you have s, so that's the diagonal. So that actually goes from one corner to the other. This is s. So for part A, we need a volume equation. So this is a box, so volume equals x, y, z. dv dt equals to, be careful with your product rule here, dx dt times yz plus dy dt times xz plus dz dt times xy. Okay, now again, these are the conditionals. So I want to find that when x is 4, y is 3, z is 2. So we'll plug all those in with our known rates of change of the sides from up here above. So plugging everything in, y times z, so 1 times 6 plus negative 2 times x times z, so 8, plus dz dt times x times y, so that's 12, and that's 6 minus 16 plus 12, we have 2 cubic centimeters per second because we're talking about the change in volume. So let's try the next one. Surface area. This is a box, 2 of each side. So that means 2 tops, which is xy, plus 2 sides, left and right, so that's zy, and then 2 of the front and back pieces, so that's xz. dsa dt equals to 2 times, it's going to get a little long here, dx dt times y plus dy dt times x plus dz dt times y, dy dt times z, plus dx dt times z, plus dz dt times x. So that'll be 2 times 1 times 3 plus negative 2 times 4 plus 1 times 3 plus negative 2 times 2 plus 1 times 2 plus 1 times 4. So 6 minus 8 plus 3 minus 4 plus 2. Let me see, these will cancel. That's 8, and the rest is 8. I get 0. Surface area does not change. And one last one to go. So that is the diagonal. S equals to the square root of x squared plus y squared plus z squared. And I'm going to implement a strategy similar to what I did on the last problem. I'm going to square everything because I don't want to have to take the derivative with that square root in there and have to deal with the power rule. So 2 times 2s ds dt equals 2x dx dt plus 2y dy dt plus 2z dz dt. So plugging in everything we know and also canceling out all these 2's, which we don't need, leaves us with ds dt equals to, so I have x, which is 4, times 1, plus y, which is 3, times dy dt, which is negative 2, plus z, which is 2, times dz dt, which is 1, all over s. Oh, and I didn't figure out what s is. S is equal to the square root of 4 squared plus 3 squared plus 2 squared. So 16 plus 9 plus 4, so square root of 29. That goes down here. Remember, it's not always square root of 29, it just happens to be on this one. So 4 minus 6 plus 2, nope, once again 0. The length of the diagonal does not change.